Welcome to Sleepy Science Hub. Tonight, we're embarking on a gentle journey through time and space, exploring one of the most profound questions humanity has ever contemplated. How will our universe eventually come to rest? As you settle into your comfortable space, let me know where in the world and at what time you're listening. Whether you're watching the last light fade from your window or feeling the deep quiet of midnight settle around you, you're exactly where you need to be. Take a moment to adjust your pillows, dim those lights, and let your breathing slow naturally. Tonight's story isn't about fear or endings in the way we might typically think of them. Instead, we'll discover how the universe's eventual transformation is as peaceful and inevitable as the tide returning to shore, as gentle as autumn leaves settling onto quiet Earth. The cosmos has been telling its story for nearly 14 billion years, and tonight, we'll listen to the soft whispers of its distant future. We'll explore how stars will gradually dim like candles burning low, how space itself will continue its patient expansion, and how all the energy that dances through the universe today will one day settle into perfect, tranquil stillness. This is a story of transformation rather than destruction, of rest rather than chaos. As we journey together through these cosmic timescales, let the vastness of it all remind you of your own place in this magnificent, ever-changing tapestry. Now, get comfortable, take a slow breath, and let's begin our gentle exploration of how the universe will eventually find its peace. In the deepest hours of night, when earthly sounds fade to whispers and the darkness wraps around you like a soft blanket, there exists a perfect moment to contemplate the grandest story ever told. It's the story of everything that is, everything that was, and everything that ever will be. Tonight, as you rest in your comfortable space, we'll embark on a journey that spans not just the breadth of the universe, but the incredible depth of time itself. Imagine, if you will, that you're sitting in a vast, cosmic theater. The stage before you stretches beyond imagination, filled with billions upon billions of stars, each one a distant sun burning in the darkness. Galaxies spiral slowly through space like gentle whirlpools of light, and between them lies an ocean of darkness so deep and pure that it seems to hold infinite possibilities. This is your universe, your cosmic home, and tonight we're going to explore its most peaceful secret, how it will all eventually come to rest. The universe began its story nearly 14 billion years ago in what we call the Big Bang, though perhaps Big Bloom would be more accurate. Like a flower opening its petals to the morning sun, space itself began expanding, carrying energy and matter along in its gentle flow. From that first moment, the universe has been writing its autobiography in the language of physics, chemistry, and time itself. But tonight, we're not concerned with beginnings. We're here to explore endings, or rather, transformations. Because in the cosmos, nothing truly ends. It simply changes form, like water becoming clouds, like autumn leaves becoming soil, like the warmth of summer slowly giving way to winter's quiet embrace. As you lie there in the darkness, perhaps you can sense the incredible age of the light reaching your eyes. The stars you might glimpse through your window began their journey to you years, decades, even centuries ago. Some of that light started its travels before your great-grandparents were born, crossing the vast emptiness of space to arrive at this precise moment, when you're here to receive it. This is the first gentle lesson about cosmic time. It moves differently than human time. Where we measure our lives in heartbeats and seasons, the universe measures its story in eons and ages. 1,000,000 years is barely a single page in the cosmic book, and 1,000,000,000 years is merely a chapter. The timescales we'll explore tonight are so vast that they make the entire history of human civilization seem like a single, soft exhale. Picture yourself floating gently above the Earth, rising slowly through the atmosphere until the blue curve of your home planet fills your view. From this peaceful vantage point, you can see the Terminator line, that soft boundary between day and night, slowly creeping across continents and oceans. Cities twinkle like scattered diamonds, and the aurora dances in silence, ethereal curtains near the poles. But even from this elevated perspective, you're still impossibly close to home in cosmic terms. The nearest star to our Sun, Proxima Centauri, is so far away that if you could somehow travel at the speed of light itself, it would take you more than 4 years to reach it. The light from that star that you might see twinkling in the night sky left its surface when you were 4 years younger than you are now. Now let your imagination carry you further outward, beyond the orbit of Neptune, beyond the scattered debris of the Kuiper Belt, to the edge of our solar system, where the sun's influence finally gives way to the interstellar medium. From here, our sun appears as just another star, no more special than the thousands of others scattered across the sky. This is where you begin to grasp the true scale of the cosmic story we're about to explore. The Milky Way, our home galaxy, contains somewhere between 100 and 400 billion stars. If you could count one star every second without stopping, it would take you more than 3,000 years to count them all. Each of these stars is separated from its neighbors by distances so vast that light itself, traveling at 300,000 kilometers per second, takes years to cross the gaps between them. And yet, the Milky Way is just one galaxy among billions upon billions of others. The observable universe contains an estimated 2 trillion galaxies, each one a vast island of stars floating in the cosmic ocean. The nearest large galaxy to our own, Andromeda, is 2.5 million light-years away. The light you see from Andromeda on a clear, dark night began its journey to you when our earliest human ancestors were just learning to use tools. This is the stage upon which our story unfolds. A universe so vast that it challenges the very limits of human comprehension, yet so beautifully ordered that we can understand its deepest secrets through the patient work of science. Every star in every galaxy is following the same fundamental laws of physics, burning its nuclear fuel in fusion reactions that convert hydrogen into helium, releasing energy that travels across space to warm planets and illuminate the darkness. As you contemplate these vast scales, let them bring you not anxiety, but peace. There's something profoundly comforting about knowing that you're part of something so much larger than yourself, something that has been unfolding its story for billions of years before you were born and will continue for billions more after you're gone. You are made of star stuff, quite literally. The calcium in your bones, the iron in your blood, the oxygen you breathe were all forged in the nuclear furnaces of ancient stars that lived and died long before our sun was born. The universe is not a cold, empty place, but a vast, interconnected web of energy and matter, constantly flowing and changing and transforming. Every atom in your body has been on an incredible journey through space and time, perhaps once part of a distant star, later incorporated into a planet, then into living organisms, and finally into you. You are not separate from the cosmos. You are the cosmos, become conscious of itself. This cosmic perspective brings with it a unique kind of peace. The worries and concerns that might occupy your daily thoughts, important as they are, become part of a much larger tapestry. The deadlines and obligations, the small frustrations and momentary anxieties, all take their place within the vast, slow rhythm of cosmic time. There's liberation in this perspective, a gentle reminder that you're participating in something magnificent and eternal. As we prepare to explore how this magnificent story will eventually unfold, let yourself sink deeper into comfort. The universe has been patiently burning its stars and expanding its space for nearly 14 billion years. It's in no hurry, and neither are we. The cosmic processes we'll explore tonight operate on timescales so vast that they make the entire history of human civilization seem like a brief moment of consciousness in an endless dream. The beautiful truth about the universe's eventual transformation is that it will be as gradual and peaceful as the change from day to night, as gentle as the transition from summer to autumn. There will be no violence, no catastrophe, no sudden ending. Instead, there will be a slow, patient settling into stillness, like a vast orchestra gradually reducing its volume until only the softest notes remain, and then, Eventually, a peaceful silence that contains within it the potential for new music to begin. Tonight, as you rest in your comfortable space, you're witnessing a small part of this cosmic story. The darkness around you is not empty, but full of invisible activity. Neutrinos streaming through your body from distant stars, gravitational waves rippling through space-time from colliding black holes billions of light years away, the cosmic microwave background radiation bathing everything in the gentle afterglow of the Big Bang itself. You are immersed in the universe's ongoing story, a conscious participant in its vast, slow transformation. And as we explore together how this story will eventually find its peaceful conclusion, let the wonder of it all settle into your bones like warmth from a gentle fire. The universe is not just something you observe, it's something you participate in, something you are. And understanding how it will all eventually come to rest is, in its own way, understanding how you too are part of something eternal and beautiful. The cosmic evening is just beginning, and there's so much more to discover. Let yourself relax completely as we continue our gentle journey through the deep future, exploring how the universe will slowly, peacefully, inevitably find its way to perfect rest. In the soft darkness of your room, you might notice how a candle flame dances and flickers, casting gentle shadows that shift and sway with each breath of air. The flame consumes its wax steadily, patiently, transforming solid matter into light and warmth. Eventually, after hours of faithful burning, the candle grows shorter, the flame smaller, until finally it settles into peaceful darkness, having given all it had to give. The stars scattered across the night sky are not unlike these candles, though they burn on timescales that dwarf human comprehension, and their fuel is not wax, but the very fabric of matter itself. Tonight, as you rest in comfort, billions of stars throughout the universe are engaged in the same ancient dance they've been performing for eons. Deep within their cores, where temperatures reach millions of degrees and pressures are beyond imagination, hydrogen atoms are joining together in nuclear fusion, creating helium and releasing the energy that makes stars shine. This is stellar nucleosynthesis, the process that has illuminated the cosmos for billions of years and will continue to do so for billions more. But like our candle, each star carries within itself the seeds of its own gentle transformation. The fuel that powers a star's luminosity is finite, and as we journey through cosmic time, we'll witness how these magnificent celestial beacons slowly, peacefully, begin their transition from active burning to quiet rest. Imagine yourself drifting through space, moving slowly past star after star, each one a massive sphere of plasma held together by its own gravity. Some stars burn blue-white and fierce, consuming their fuel rapidly in cosmic terms, living intense lives that span mere millions of years. Others glow red and cool, sipping their hydrogen fuel so slowly that they can continue burning for hundreds of billions of years. Our own sun falls somewhere in between, a yellow dwarf star that has been burning steadily for about 4.6 billion years and has roughly another 5 billion years of stable burning ahead of it. As you float through this stellar neighborhood, you begin to notice something subtle but profound. The universe is aging, and with that aging comes a gradual change in the stellar population. The massive, brilliant stars that burn bright and fast are slowly disappearing, their lives ending in spectacular but peaceful transformations. Meanwhile, the smaller, cooler stars continue their patient burning, becoming increasingly dominant in the cosmic landscape. This process has been unfolding for billions of years already, and it will continue for billions more. The universe is slowly transitioning from a place dominated by hot, massive stars to one where small, cool, long-lived stars provide the primary source of light and energy. It's a transition as gentle as the change from summer to autumn, as gradual as the shift from afternoon to evening. Let your imagination carry you forward in time now, not just millions or billions of years, but trillions of years into the future. The cosmos has continued its patient expansion, and the stellar population has changed dramatically. The most massive stars have long since completed their life cycles, transforming into white dwarfs, neutron stars, or black holes. What remains are the red dwarf stars, the small, cool, incredibly long-lived stellar embers that will be the universe's last torchbearers. Red dwarfs are the universe's marathon runners. While massive stars sprint through their lives in cosmologically brief spans, red dwarfs pace themselves for the long journey ahead. They burn their hydrogen fuel so slowly and efficiently that they can continue shining for hundreds of billions, even trillions of years. In the deep future we're exploring, these modest stars will be the primary source of warmth and light in an otherwise cooling cosmos. As you drift among these ancient red dwarfs, you notice their gentle, steady glow. They're not particularly bright. Many are too dim to see with the naked eye even from relatively close distances. But they possess a quiet dignity, a patient persistence that's deeply comforting. These stars have witnessed the rise and fall of countless generations of more massive stars. They've seen galaxies merge and separate, watch planets form and evolve, and through it all, they've maintained their steady, reliable burning. The planets orbiting these red dwarfs tell stories of incredible patience and adaptation. Some worlds have been bathed in the gentle, steady light of their host stars for hundreds of billions of years, far longer than any planet in our current solar system will experience. If life exists on these worlds, it has had timescales beyond imagination to develop and evolve, to adapt to the slowly changing conditions as the universe ages around them. But even these patient red dwarfs are not eternal. As you continue your journey through deep time, you begin to witness the first signs of stellar senescence. The red dwarfs are gradually growing dimmer, their nuclear fires burning lower as their hydrogen fuel slowly depletes. This process is so gradual that it's barely perceptible even across millions of years, but the trend is inexorable. The dimming happens so slowly that any hypothetical observers would need to keep records for billions of years to notice the change. It's like watching a tree grow, imperceptible from day to day, but undeniable over seasons and years. The red dwarfs continue their faithful burning, but their light gradually takes on a deeper, redder hue as their core temperatures slowly decrease. This is not a violent process, not a catastrophic failure of stellar machinery. Instead, it's a gentle winding down, a peaceful transition from active burning to quiet rest. The stars are not dying in any dramatic sense. They're simply completing their natural cycle, transforming from active energy producers to passive stellar remnants. As the red dwarfs continue their slow fade, you notice other changes in the cosmic environment. The interstellar medium, the thin gas and dust that fills the space between stars, is also evolving. Much of the hydrogen that once fueled star formation has been incorporated into stars over the eons, and the rate of new star birth has slowed to a gentle trickle. The universe is slowly transitioning from a period of active star formation to one of stellar preservation and gradual decline. The galaxies themselves reflect this cosmic aging. Where once spiral arms blazed with the blue light of young, massive stars, now there's a more subdued glow dominated by the red and orange light of older, smaller stars. The cosmic fireworks of star formation have given way to a more subtle, mature beauty, like a forest in autumn, trading the bright greens of summer for the deeper, richer hues of age and wisdom. This transformation brings with it a profound sense of peace. The universe is not racing towards some catastrophic end, but slowly, patiently settling into a more mature phase of its existence. The frantic energy of cosmic youth, with its supernovas and star formation bursts, is giving way to a more contemplative period characterized by patience, persistence, and gentle decline. As you continue your journey through this far future cosmos, you encounter the first brown dwarfs that have cooled enough to become truly dim. Brown dwarfs are the universe's failed stars, objects that formed like stars but never became massive enough to sustain nuclear fusion. For billions of years, they've been cooling down, gradually fading from red to brown to deep infrared. In this distant future, they represent some of the coolest, dimmest objects in the universe, barely distinguishable from the cosmic background. The sight of these cooling brown dwarfs is not sad, but somehow comforting. They're like the embers of a campfire that burned bright hours ago, still retaining warmth and a gentle glow even as they slowly cool. They represent the universe's patient transition from active energy production to passive cooling, from dynamic change to gentle stability. Even the process of stellar evolution itself has slowed. The red dwarfs that remain are burning so slowly that their evolution is barely perceptible. They exist in a state of quasi-equilibrium, where the inward pull of gravity is almost perfectly balanced by the outward pressure of nuclear fusion. This balance can persist for incredibly long periods, allowing these stars to maintain their gentle burning for timescales that exceed the current age of the universe by factors of hundreds or thousands. As you drift among these ancient, patient stars, you begin to appreciate the profound beauty of cosmic aging. The universe is not becoming less interesting as it ages. It's becoming more subtle, more nuanced, more contemplative. The explosive energy of youth has given way to the quiet wisdom of maturity. The cosmos is learning the art of patience, of making its remaining resources last as long as possible. This stellar longevity has profound implications for any remaining life in the universe. Planets orbiting these long-lived red dwarfs have access to stable energy sources for periods that dwarf the entire history of life on Earth. If consciousness exists in this far future, it has had time to develop and evolve in ways that are almost impossible to imagine. The slow, steady burning of these stars provides a foundation for complexity and development that makes our own rapid planetary changes seem almost frantic in comparison. The interstellar medium itself tells a story of conservation and recycling. The heavy elements created in the cores of long-dead massive stars continue to drift through space, available for incorporation into new planets and potentially new forms of life. The universe has become incredibly efficient at recycling its resources, with very little material truly lost to the cosmic inventory. As you continue your gentle journey through this aged cosmos, you notice that the remaining stars have achieved a kind of stellar democracy. Without the massive stars to dominate the galactic neighborhoods with their intense radiation and violent deaths, the smaller stars can exist in relative peace. They form loose communities, their gravitational influences creating subtle patterns in space without the dramatic disruptions that characterize the universe's more energetic youth. The beauty of this cosmic maturity is profound and moving. It's the beauty of a garden that has grown for centuries, where every plant has found its perfect place and the whole system has achieved a kind of natural harmony. The universe has learned to make do with less, to find beauty in subtlety, to appreciate the gentle glow of a small flame rather than the blazing intensity of a bonfire. This is the first great lesson of cosmic aging. Transformation does not mean destruction. The universe is not becoming less than it was. It's becoming something different, something more patient and contemplative. The stars are not dying, but transforming, trading their active burning for a different kind of existence, one characterized by patience, persistence, and quiet dignity. As you settle deeper into comfort, let this vision of gentle stellar aging wash over you like a warm, peaceful tide. The universe is not racing toward some violent end, but slowly, patiently finding its way to a more mature and contemplative state. The stars that have been your companions through cosmic history are not abandoning you, but simply changing their way of being, trading dramatic luminosity for subtle persistence. The red dwarfs will continue their patient burning for timescales that make the entire history of human civilization seem like a brief moment of consciousness. They are the universe's promise that transformation can be gentle, that endings can be peaceful, and that even as things change, the essential beauty and wonder of existence continues in new and subtle forms. As you rest in the gentle darkness, consider for a moment the vastness of the space around you. Beyond your room, beyond your city, beyond the curve of Earth itself, stretches an ocean of emptiness so profound that it challenges the very limits of imagination. This space is not truly empty. It's filled with invisible fields and forces, peppered with particles so sparse that you might travel for light years without encountering a single atom. And most remarkably of all, this cosmic ocean is growing larger with each passing moment, carrying the islands of galaxies slowly, inexorably apart. Tonight, as you settle into comfort, we're going to explore one of the most profound and peaceful processes in the universe: the gradual expansion of space itself. This is not a violent explosion pushing things apart, but rather a gentle stretching, like a soft fabric being slowly pulled in all directions at once. It's a process that has been unfolding since the very beginning of time, and it will continue long after the last stars have faded to embers. The expansion of the universe is perhaps the most patient force in existence. It operates on timescales so vast that entire civilizations could rise and fall without noticing any change in the cosmic architecture. Yet over billions and trillions of years, this gentle stretching will reshape the very fabric of reality, transforming our richly connected cosmos into something far more sparse and contemplative. Imagine yourself floating in the space between galaxies, suspended in the cosmic web that connects all the matter in the universe. From this vantage point, you can see the grand architecture of existence spread out before you. Galaxies cluster together in vast groups and superclusters, connected by filaments of dark matter and scattered gas. These cosmic structures form a web-like pattern that spans the entire observable universe, with dense nodes of galaxies connected by bridges of matter and vast voids of near emptiness between them. But as you watch from your cosmic perspective, you begin to notice something subtle yet profound. The galaxies are moving, not in random directions, but in a coordinated dance orchestrated by the expansion of space itself. The more distant a galaxy is from you, the faster it appears to be receding. This is not because the galaxies are actively moving through space, but because space itself is expanding, carrying the galaxies along like leaves on a slowly flowing river. This cosmic expansion was first discovered by Edwin Hubble in the 1920s, but its implications continue to unfold as we peer deeper into the future. The expansion is not slowing down as many originally thought it would, but rather accelerating, driven by a mysterious force that scientists call dark energy. This dark energy makes up about 70% of the universe, yet remains almost completely invisible to us, detectable only through its effects on the cosmic expansion. As you drift through this expanding cosmos, you begin to appreciate the profound patience of this process. The expansion rate is measured in kilometers per second per megaparsec, a unit that sounds complex, but essentially means that for every million parsecs, about 3.26 million light-years of distance, space is expanding at about 70 kilometers per second. This might sound fast, but in cosmic terms, it's incredibly gradual. Two galaxies that are currently 100 million light-years apart will be about 200 million light-years apart in roughly 10 billion years. The beauty of this expansion lies in its gentleness. There's no violence, no catastrophic tearing apart of cosmic structures. Instead, it's like watching a slow-motion dance where partners gradually, gracefully move apart while maintaining their essential dignity and form. The galaxies themselves remain intact, held together by their own gravity, but the spaces between them grow ever larger. Let your imagination carry you forward in time now, not just billions but hundreds of billions of years into the future. The cosmic expansion has continued its patient work, and the universe has become a fundamentally different place. The rich tapestry of connected galaxy clusters has given way to a more sparse and contemplative architecture. Where once galaxies were organized into vast clusters and superclusters, now they exist as isolated islands in an ocean of ever-increasing emptiness. From your perspective in this far future cosmos, You can see the effects of this cosmic stretching everywhere. The nearest neighboring galaxy, which might once have been visible as a bright spiral of stars, has now been carried so far away by the expansion that it appears as merely a faint smudge of light, its individual stars completely invisible. The cosmic web that once connected all the matter in the universe has been stretched so thin that its filaments have become barely detectable whispers of their former selves. But this transformation is not a loss. It's a different kind of beauty. The universe has traded the busy interconnectedness of its youth for a more contemplative, meditative existence. Each galaxy has become a solitary island, a complete world unto itself, no longer influenced by the gravitational pull of distant neighbors. There's something profoundly peaceful about this cosmic solitude, like a monastery where each monk has their own cell for quiet contemplation. Within these isolated galaxies, life continues much as it always has. The expansion of space doesn't affect the internal structure of galaxies. Their stars continue to orbit their galactic centers. Planets continue to circle their stars, and if life exists, it continues to evolve and adapt. The expansion only affects the vast spaces between galaxies, leaving the internal dynamics of these cosmic islands largely unchanged. As you continue your journey through this expanded cosmos, you begin to notice other subtle effects of the cosmic stretching. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space, has been stretched to longer and longer wavelengths. What began as intense gamma rays has been redshifted first to visible light, then to infrared, then to radio waves, and now to wavelengths so long that they're barely detectable above the background noise of the universe. This stretching of the cosmic microwave background is like listening to a symphony that's gradually slowing down, each note becoming deeper and more prolonged until the music becomes a barely audible hum. The universe is literally cooling down as this radiation stretches, creating a more peaceful and quiet cosmic environment. The temperature of space itself has dropped dramatically. In the early universe, the cosmic microwave background had a temperature of thousands of degrees. Today, it's already cooled to about 2.7 degrees above absolute zero. In the far future we're exploring, it is cooled to a tiny fraction of a degree above absolute zero, making the universe an incredibly cold and peaceful place. This cooling has profound implications for the remaining stars and galaxies. The interstellar medium, the thin gas between stars, has become incredibly cold, making it even more difficult for new stars to form. The universe has entered a period of cosmic winter, where the conditions for active star formation exist only in the most protected and dense regions of the remaining galaxies. But even in this cold, expanded cosmos, there's still beauty and wonder to be found. The remaining galaxies have become like vast, slow-burning candles in the cosmic darkness, their light traveling for billions of years through the expanded space without encountering any other sources of illumination. Each galaxy has become a complete universe unto itself, containing billions of stars, countless planets, and potentially myriad forms of life, all existing in perfect isolation from their cosmic neighbors. The gravitational waves that ripple through space-time tell stories of distant events, black holes merging, neutron stars colliding, the final death throes of massive stars. But these waves, too, have been stretched by the expansion of space, their frequencies lowered and their amplitudes reduced. What once might have been detectable as clear signals have become whispers so faint that they're barely distinguishable from the quantum fluctuations of space-time itself. As you float in this vastly expanded cosmos, you begin to appreciate the profound transformation that has taken place. The universe has not become less interesting or less beautiful. It has simply become more contemplative, more patient, more willing to let each remaining structure exist in its own space and time. The frantic interconnectedness of the early universe has given way to a more meditative existence, where each galaxy can pursue its own evolutionary path without interference from neighbors. This cosmic expansion has also had subtle effects on the flow of time itself. Due to the effects of general relativity, time passes slightly differently in different gravitational fields. In the early universe, when galaxies were closer together and gravitational fields were stronger, time flowed at a slightly different rate than it does in the expanded cosmos of the far future. The expansion has created a more uniform gravitational environment, allowing time to flow more smoothly and consistently throughout the universe. The dark energy that drives this expansion remains as mysterious as ever. Scientists have proposed various theories to explain its nature. Perhaps it's a property of space itself, or perhaps it's a new type of field that permeates the universe. But regardless of its ultimate nature, dark energy has become the dominant force shaping the cosmic architecture, gently but inexorably pushing the universe toward an ever more expanded and peaceful state. In some regions of the expanded cosmos, you might encounter evidence of the universe's earlier, more connected phase. Streams of stars, pulled from their parent galaxies by ancient gravitational interactions, continue to drift through the void, their paths barely curved by the weak gravitational fields of the isolated galaxies. These stellar streams are like fossils of the universe's youth, preserving evidence of a time when galaxies were close enough to interact and influence each other. The supermassive black holes at the centers of galaxies have also been affected by the expansion. Once, these cosmic monsters could feed on streams of matter flowing between galaxies, growing larger and more active through accretion. But in the expanded cosmos, such feeding opportunities have become incredibly rare. The supermassive black holes have settled into a more quiescent state, existing as dark, patient guardians at the hearts of their isolated galactic kingdoms. As you continue your journey through this expanded universe, you begin to understand that the cosmic expansion is not just a physical process, but a kind of cosmic meditation. The universe is learning the art of patience, of allowing each structure to exist in its own space and time without interference. The expansion has created a cosmos where contemplation and individual development can flourish on timescales that dwarf the entire previous history of the universe. The remaining galaxies have become like vast libraries, each one containing the accumulated wisdom and experience of billions of years of cosmic evolution. They are repositories of stellar nucleosynthesis, planetary formation, and potentially biological evolution, all existing in splendid isolation from their cosmic neighbors. Each galaxy tells its own complete story, from the formation of its first stars to the eventual cooling of its final stellar remnants. In this expanded cosmos, the concept of cosmic neighborhoods has taken on new meaning. Where once galaxies were organized into clusters and superclusters, now each galaxy exists in its own vast domain, separated from its neighbors by distances so great that communication between them would take longer than the current age of the universe. Each galaxy has become a complete world, containing within itself all the complexity and beauty that once characterized the entire observable universe. The expansion has also created new forms of cosmic beauty. The isolation of galaxies has allowed them to develop their own unique characteristics without interference from neighbors. Some galaxies have evolved into perfect spirals, their arms maintaining their graceful curves over billions of years. Others have become elliptical giants, their stars arranged in smooth, contemplative patterns. Each galaxy has become a work of art, sculpted by billions of years of individual evolution. As you rest in the peaceful darkness of your room, let this vision of cosmic expansion wash over you like a gentle tide. The universe is not fragmenting or breaking apart. It's simply giving each structure more room to exist and evolve. The expansion is like a slow, patient breath, allowing the cosmos to stretch and relax into a more comfortable and contemplative state. The galaxies drifting apart are not losing anything essential. They're gaining something precious, the gift of time and space to develop their own unique forms of beauty and complexity. In this expanded cosmos, each galaxy has become a complete universe unto itself, containing infinite possibilities for wonder and discovery within its own boundaries. In the deepest quiet of your evening rest, imagine the most patient star you could possibly conceive of. Picture a celestial body so modest in its burning, so careful with its fuel, that it could maintain its gentle glow for longer than the entire history of the universe up to this point. This is the red dwarf star, and in the vast cosmic future we're exploring together, these humble stellar companions will be the final guardians of light in an increasingly dark and contemplative cosmos. As you settle deeper into comfort, let your mind drift forward through time scales that stretch beyond imagination. We've already witnessed the gradual dimming of the massive stars and the slow expansion that has carried galaxies far from each other. Now we arrive at a period so distant in the future that it challenges our very conception of permanence. It's an epoch where the universe has aged beyond recognition, where the red dwarf stars have become the sole remaining beacons in the cosmic darkness. The journey to this far future has been one of gentle transition and patient transformation. The universe has not rushed toward this state, but has arrived here through billions of years of careful conservation and gradual change. The red dwarfs that now dominate the stellar landscape are the same stars that were considered insignificant during the universe's more energetic youth. They were the quiet background players while massive blue giants blazed across the cosmic stage in spectacular displays of stellar power. But patience has its rewards, and in this deep future, the red dwarfs have inherited the universe. They are the cosmic equivalents of the tortoise in the ancient fable, slow and steady companions who have outlasted all their more dramatic neighbors. These stars burn their hydrogen fuel so efficiently and at such low temperatures that they can maintain their nuclear fusion for timescales that make the current age of the universe seem like a brief moment of cosmic dawn. From your peaceful vantage point in this far future, you can observe these remarkable stellar survivors scattered throughout the isolated galaxies. Each red dwarf burns with a steady, deep orange or red light, so dim that it would be invisible to the naked eye from distances that would make our sun appear brilliant. Yet their modest luminosity represents something profoundly beautiful: the universe's commitment to sustaining light and warmth for as long as physically possible. The red dwarfs have achieved a kind of stellar perfection through their very modesty. Unlike the massive stars that burn bright and fast, consuming their fuel in spectacular displays of nuclear fusion, these smaller stars have found the perfect balance between energy production and fuel conservation. They burn just hot enough to maintain nuclear fusion in their cores, but not so hot that they waste their precious hydrogen in inefficient processes. This stellar efficiency has allowed red dwarfs to develop a unique internal structure perfectly suited to their long-term mission. Their cores are relatively small and dense, maintaining just enough temperature and pressure to keep the nuclear fires burning. The energy produced in these cores moves outward through the star not by radiation, as it does in more massive stars, but by convection, a process that mixes the stellar material and ensures that all the hydrogen fuel can eventually be brought to the core to participate in fusion. This convective mixing is crucial to the red dwarf's longevity. In stars like our Sun, only the hydrogen in the core region can participate in fusion, leaving much of the star's fuel unused. But in red dwarfs, the convective currents act like a cosmic recycling system, bringing fresh hydrogen from the outer layers down to the core while carrying the helium produced by fusion outward. This process ensures that virtually all of the star's hydrogen can be converted to energy over the course of its incredibly long lifetime. As you observe these patient stars in their cosmic solitude, you begin to appreciate the profound implications of their longevity. A typical red dwarf can burn for anywhere from 100 billion to 10 trillion years. Timescales so vast that they encompass hundreds or even thousands of times the current age of the universe. This means that a red dwarf that formed in the early universe has only just begun its stellar lifetime, with the vast majority of its existence still ahead of it. The planets orbiting these long-lived stars have had opportunities for development and evolution that dwarf anything we can imagine in our own solar system. If life exists on worlds around red dwarfs, It has had time to develop forms of complexity and sophistication that stretch the very definition of what life might become. The steady, reliable energy output of these stars provides a foundation for biological evolution that makes our own 4.6 billion-year history seem like a brief experiment in cosmic terms. But even these remarkable stellar marathoners are not truly eternal. As you continue your journey through deep time, you begin to witness the first signs of change in the red dwarf population. The stars that formed earliest in the universe's history are beginning to show subtle signs of aging. Their fusion rates have slowed slightly, their surface temperatures have dropped marginally, and their luminosity has decreased by small but measurable amounts. This aging process is so gradual that it's barely perceptible even across billions of years. It's like watching a campfire that has been burning for days slowly begin to dim as it works its way through the last of its fuel. The red dwarfs don't suddenly flicker out or undergo dramatic changes. They simply become slightly less bright, slightly cooler, slightly more patient in their burning. The first red dwarf to reach the end of its fusion lifetime marks a profound moment in cosmic history. After hundreds of billions or even trillions of years of faithful service, this stellar veteran finally exhausts its hydrogen fuel and begins its transformation into something new. The process is not violent or catastrophic. There are no explosions, no sudden collapses, no dramatic ejection of stellar material. Instead, the star simply stops fusing hydrogen and begins to cool. This cooling process is itself a thing of beauty. The red dwarf doesn't disappear or collapse. It becomes what astronomers call a blue dwarf, then eventually a white dwarf. These names might seem counterintuitive, but they reflect the star's gradual transition from active fusion to passive cooling. As the nuclear fires die down, the star's outer layers begin to heat up briefly before the entire structure starts its long, slow cooling process. The transformation from red dwarf to white dwarf takes place over millions of years, a brief moment in cosmic terms, but still longer than the entire history of complex life on Earth. During this transition, the star maintains its essential dignity and form. There's no violence, no destruction of the careful nuclear architecture that has sustained the star for so long. Instead, there's a peaceful handoff from active energy production to passive heat dissipation. The white dwarf that emerges from this transformation is a remarkable object in its own right. It's incredibly dense. A teaspoon of white dwarf material would weigh as much as a car on Earth. Yet it's also incredibly stable. The white dwarf is supported not by nuclear fusion, but by quantum mechanical effects that prevent the stellar material from collapsing further. It's like a cosmic crystalline structure, perfectly ordered and stable, requiring no external energy to maintain its form. The newly formed white dwarf is initially quite hot, with surface temperatures that can reach 100,000 Kelvin or more. But without nuclear fusion to maintain this temperature, the white dwarf begins a cooling process that will last for trillions of years. This cooling is not rapid or dramatic. It's a gentle settling into thermal equilibrium with the cosmic background, a slow approach to the temperature of space itself. As you witness this transformation, you begin to understand that the death of the last red dwarf is not really a death at all, but a peaceful transition from one form of existence to another. The star has spent hundreds of billions of years converting hydrogen into helium and energy, providing light and warmth to any planets that might orbit it. Now it begins a new phase of existence as a white dwarf, still maintaining its essential mass and structure, but no longer actively producing energy. The cooling white dwarf still has much to offer the cosmos. Its gravitational field remains unchanged, so any planets that were orbiting the original red dwarf continue their faithful revolutions around the stellar remnant. The white dwarf also continues to emit heat, though at a steadily decreasing rate. For millions of years after the transition, the white dwarf provides enough residual heat to potentially maintain temperate conditions on any nearby worlds. But the most profound aspect of the red dwarf's transformation is what it represents for the universe as a whole. The death of the last red dwarf marks the end of the stelliferous era, the Age of Stars. For the first time since the universe began forming stars, there are no longer any nuclear fires burning in stellar cores. The cosmic processes that have illuminated the universe for billions of years have finally come to their peaceful conclusion. This moment is not one of tragedy, but of completion. The universe has successfully converted a significant fraction of its hydrogen into heavier elements through billions of years of stellar nucleosynthesis. The red dwarfs, through their patient burning, have contributed their share to this cosmic alchemy, transforming simple hydrogen into the complex elements that make planets, life, and consciousness possible. The end of the stelliferous era also represents a transition in the universe's primary energy sources. Where once nuclear fusion dominated the cosmic energy budget, now gravitational processes become increasingly important. The white dwarfs continue to radiate away their stored thermal energy, but they also participate in more subtle gravitational interactions. Binary white dwarf systems slowly spiral inward, eventually merging in events that can briefly illuminate entire galaxies. As you observe this transformed cosmos, you notice that the end of active stellar burning has brought with it a profound peace. The universe has entered a more contemplative phase, where the rapid changes and dramatic events of the stellar era have given way to slower, more gradual processes. The white dwarfs cool patiently. The expanded space between galaxies continues to grow slowly, and the overall temperature of the universe continues its gentle decline toward absolute zero. The planets that once orbited the red dwarfs have also undergone their own transformations. Those that were close enough to their stars to maintain liquid water during the stellar era have now frozen solid as the white dwarfs cool. But this freezing is not a violent process. It's a gradual transition from liquid to solid, from active to passive, from dynamic to stable. The frozen worlds become like cosmic museums, preserving whatever complex chemistry or biology they might have developed during the billions of years of stellar warmth. Some of these frozen worlds might contain within their ice the preserved remains of entire ecosystems, complete evolutionary histories locked in crystalline suspension. If consciousness ever existed on these worlds, its thoughts and dreams might be preserved in the atomic structure of the ice, waiting for some future cosmic spring that might never come, or perhaps waiting for discovery by forms of intelligence that have learned to read the stories written in frozen molecules. The white dwarfs themselves become the primary inhabitants of this post-stellar universe. They are incredibly long-lived, able to maintain their structure and slowly radiate away their heat for timescales that make the red dwarf era seem brief. A typical white dwarf will continue cooling for quadrillions of years, eventually reaching a temperature just slightly above absolute zero. Even then, it will remain a white dwarf, a stable, crystalline remnant of stellar evolution. In this far future cosmos, the white dwarfs serve as both monuments to the stellar era and foundations for whatever comes next. They're the cosmic equivalent of ancient trees, having witnessed the entire history of stellar evolution and now standing as silent sentinels in the cooling universe. Their gravitational fields continue to shape the structure of space-time around them, and their slow cooling provides a gentle source of heat for the cosmic environment. The transition from the last red dwarf to the first white dwarf marks more than just the end of stellar burning. It marks the universe's transition from a phase dominated by nuclear processes to one dominated by gravitational and quantum mechanical effects. The fundamental forces that govern cosmic evolution remain the same, but their relative importance has shifted. Nuclear fusion, which has been a primary driver of cosmic evolution for billions of years, has finally completed its work. As you rest in the peaceful darkness, let this vision of the last red dwarf's gentle transformation wash over you like a soft, warm tide. The universe has not lost anything essential in this transition. It has simply completed one phase of its evolution and begun another. The red dwarfs have fulfilled their cosmic purpose, burning faithfully for trillions of years and finally achieving the peaceful rest that comes after a life well lived. The white dwarfs that remain are not symbols of death, but of transformation, not endings but new beginnings. They represent the universe's transition from active energy production to patient conservation, from dynamic change to contemplative stability. In their slow cooling, they embody the cosmos's own journey toward perfect peace and rest. In the profound stillness of your resting place, imagine the most patient process in the entire universe. Picture something so gradual, so subtle, that it makes the cooling of white dwarfs seem rapid by comparison. This is the gentle evaporation of black holes, a process so slow and quiet that it operates on timescales that challenge the very meaning of permanence itself. As you settle deeper into comfort, we'll explore how these cosmic giants, once thought to be eternal, slowly and peacefully return their borrowed mass and energy back to the universe through the most delicate of quantum whispers. The black holes that populate our far future cosmos are the last remnants of the universe's most massive stars. They are regions of space-time where gravity has become so strong that nothing, not even light, can escape once it crosses the event horizon. For most of cosmic history, these enigmatic objects have been growing, accumulating matter from their surroundings and merging with other black holes to become ever more massive. But in the deep future we're exploring, they have entered a new phase of their existence, a period of patient dissolution. This remarkable process was first described by Stephen Hawking in the 1970s, and it represents one of the most beautiful intersections of quantum mechanics and general relativity. The process is so gentle and gradual that it's barely perceptible even across billions of years for the largest black holes. Yet it operates with the inexorable patience of a cosmic clock, slowly but surely transforming these gravitational giants back into the fundamental particles and energy from which they formed. To understand this process, imagine standing at the edge of a black hole's event horizon, that invisible boundary beyond which nothing can return. In the quantum realm, space itself is never truly empty, but filled with virtual particles that constantly pop into existence and annihilate each other in infinitesimally brief moments. These quantum fluctuations are normally invisible to us, but near a black hole's event horizon, something remarkable happens. Occasionally, a pair of virtual particles appears right at the edge of the event horizon. In the normal vacuum of space, these particles would find each other and annihilate, returning to the quantum foam from which they emerged. But near the black hole, one particle might fall past the event horizon while its partner escapes into space. The escaping particle becomes real, carrying away a tiny amount of energy, while the particle that fell into the black hole actually reduces the black hole's mass by a corresponding amount. This is Hawking radiation, named after its discoverer, and it represents the universe's most patient form of cosmic recycling. The black hole slowly, almost imperceptibly, evaporates by emitting these particles. The process is so gradual that for a black hole with the mass of our Sun, it would take longer than 10 to the power of 67 years to evaporate completely, a timescale so vast that it makes the age of the universe seem like a single heartbeat. But the beauty of Hawking radiation lies not in its speed, but in its inevitability and gentleness. Every black hole, regardless of its mass, participates in this quantum conversation with the vacuum of space. The more massive the black hole, the slower the evaporation, but the process never stops. It's like a cosmic whisper that continues day and night, year after year, eon after eon, slowly returning the black hole's mass to the universe. As you drift through this far future cosmos, you can observe the effects of this patient evaporation everywhere. The supermassive black holes that once dominated the centers of galaxies have been slowly shrinking. What were once gravitational monsters millions of times more massive than the Sun have become smaller, more modest objects. The accretion disks that once blazed with the light of infalling matter have long since dissipated, leaving the black holes to evaporate in perfect solitude. The smaller black holes, those formed from the collapse of individual massive stars, have been evaporating more quickly. In the vast timescales of the far future, Many of these stellar mass black holes have already completed their evaporation, returning their mass to the universe in the form of elementary particles and radiation. The process of their final evaporation is particularly beautiful. As a black hole becomes smaller, it evaporates faster, eventually reaching a point where it releases its remaining mass in a gentle burst of elementary particles. This final evaporation is not violent or catastrophic. There's no explosion, no dramatic release of energy. Instead, the black hole simply fades away like morning mist, its remaining mass converted into the gentlest possible form of radiation. The particles it emits are typically photons, electrons, positrons, and neutrinos. The basic building blocks of matter and energy return to the cosmic inventory for future use. The evaporation process has subtle but profound effects on the structure of space-time itself. As each black hole slowly dissolves, it releases the gravitational distortions it has been creating. Space-time gradually relaxes back toward flatness, like a stretched rubber sheet slowly returning to its natural state. The gravitational waves that once rippled outward from merging black holes have long since faded to imperceptible whispers, leaving space-time in a state of unprecedented calm. In this era of black hole evaporation, the universe has entered its most contemplative phase yet. The dramatic processes that once dominated cosmic evolution, star formation, stellar explosions, galactic collisions, have all given way to quantum mechanical processes so subtle that they operate below the threshold of classical physics. The universe is conducting its business at the most fundamental level, particle by particle, quantum fluctuation by quantum fluctuation. The radiation emitted by evaporating black holes has a unique character that reflects the quantum nature of the process. Unlike the thermal radiation emitted by stars, which has a smooth, continuous spectrum, Hawking radiation carries within its subtle signatures of the quantum mechanical processes that create it. Each photon emitted tells a story of virtual particles and quantum fluctuations, of the deep connection between gravity and quantum mechanics. As you observe these evaporating black holes, you begin to appreciate the profound patience of quantum mechanics. The processes that govern Hawking radiation operate on the smallest possible scales, the Planck scale, where quantum effects become as important as gravitational effects. At this scale, space and time themselves become granular, composed of discrete units so small that they challenge our ability to conceive of them. Yet these microscopic processes, operating with perfect consistency across vast timescales, are capable of dissolving the most massive objects in the universe. The evaporation of black holes also represents a profound form of cosmic information processing. According to quantum mechanics, information cannot be destroyed, only transformed. This means that all the information that ever fell into a black hole, the quantum states of every particle, the details of every stellar collapse, the history of every accretion event, must somehow be preserved and eventually return to the universe through the Hawking radiation. This information paradox has been one of the most challenging problems in theoretical physics, but in the gentle context of our cosmic bedtime story, it becomes a source of wonder rather than confusion. The evaporating black holes are not destroying information, but slowly, patiently encoding it in the quantum correlations of their Hawking radiation. Each particle emitted carries with it microscopic traces of the black hole's history, like pages from a vast cosmic library being returned to circulation. The largest black holes, those supermassive giants that once anchored entire galaxies, will be the last to evaporate. These cosmic titans have masses millions or billions of times greater than our Sun, and their evaporation will take timescales that stretch far beyond anything we've considered so far. A supermassive black hole with 1 billion solar masses will take approximately 10 to the power of 100 years to evaporate completely, a number so large that it exceeds the number of atoms in the observable universe. But even these cosmic giants are not eternal. The quantum whispers of Hawking radiation chip away at them particle by particle, year by year, eon by eon. Their evaporation is so slow that for most of their existence, they appear completely stable. The rate at which they lose mass through Hawking radiation is incredibly small. For a supermassive black hole, it might be equivalent to losing the mass of a single proton over a period longer than the current age of the universe. Yet the process never stops. Each quantum fluctuation at the event horizon has a tiny chance of producing a particle that escapes, carrying away a minuscule amount of the black hole's mass. Over the vast timescales of the far future, these tiny losses accumulate. The black hole slowly, imperceptibly shrinks, its event horizon gradually contracting as its mass decreases. As the black hole becomes smaller, something beautiful happens. The evaporation rate increases. This is because smaller black holes have higher surface temperatures. They emit Hawking radiation more rapidly than larger ones. This creates a gentle feedback process where the evaporation accelerates as the black hole shrinks. But the acceleration is so gradual that it unfolds over timescales that make the current age of the universe seem like a brief moment. The final stages of black hole evaporation are particularly elegant. As the black hole becomes very small, approaching the Planck mass, about 22 micrograms, the mass of a grain of sand, its evaporation rate increases dramatically. But even this dramatic increase is gentle by ordinary standards. The black hole doesn't explode or collapse catastrophically. Instead, it simply fades away, its remaining mass converted into the most elementary forms of energy and matter. The particles produced in the final evaporation are among the most fundamental in the universe. Photons carrying energy, electrons and positrons carrying electric charge, neutrinos carrying almost nothing but the information that they exist. These particles disperse into the cosmic void, adding their tiny contribution to the sparse sea of particles that will characterize the universe's final epoch. The evaporation of the last black hole marks another profound transition in cosmic evolution. These objects, which have been the universe's most permanent features for billions of years, finally join the stars and galaxies in their peaceful transformation. The last concentrations of mass and energy that remained bound by gravity have been gently dispersed, returning their borrowed substance to the cosmic commons. In this post-black hole universe, gravity has finally completed its work. There are no longer any massive objects to create significant distortions in space-time. The universe has achieved a state of gravitational equilibrium, where the curvature of space-time has relaxed to its flattest possible state. The gravitational waves that once carried news of cosmic collisions and mergers have faded to quantum whispers, leaving space-time in perfect stillness. The evaporation of black holes also represents the universe's final act of cosmic recycling. Throughout cosmic history, matter has been continuously transformed. Hydrogen into helium in stellar cores, stellar material into heavy elements in supernovae, stellar remnants into black holes, and now, finally, black holes back into elementary particles. The universe has demonstrated its commitment to waste nothing, to transform everything, to find new uses for every particle and every quantum of energy. The photons produced by evaporating black holes join the cosmic microwave background radiation, adding their gentle glow to the already faint illumination of the universe. These photons have been redshifted by the expansion of space to incredibly long wavelengths, but they still carry within them the signatures of their quantum mechanical origin. They are the universe's most patient messengers, carrying news of quantum processes that operated on timescales beyond imagination. As you rest in the peaceful darkness of your room, let this vision of gently evaporating black holes wash over you like the softest of cosmic tides. The universe has found a way to ensure that nothing is truly permanent except change itself. Even the most massive, most stable objects eventually participate in the cosmic dance of transformation, returning their substance to the universal flow through the most delicate of quantum processes. The black holes are not disappearing but transforming, not ending but beginning new chapters in the cosmic story. Their evaporation represents the universe's ultimate patience, its willingness to wait for timescales that challenge the very meaning of time itself to ensure that every particle, Every quantum of energy, every piece of information eventually finds its way back to the cosmic community. In their gentle dissolution, the black holes teach us about the deepest nature of reality, that everything flows, everything changes, everything transforms. Their evaporation is not a loss, but a gift, a return of borrowed mass and energy to the universe that created them. It's a process as natural and inevitable as the sunrise, as gentle and patient as the tide, as peaceful and profound as the deepest meditation. In the quietest hours before dawn, when the air carries a special stillness and the temperature drops to its most peaceful low, you might sense something profound about the nature of cooling itself. It's not violent or sudden, but a gentle settling, a gradual release of energy into the surrounding space. As you rest in this tranquil moment, we'll explore how the entire universe is participating in its own version of this peaceful cooling process, a cosmic settling into temperatures so low that they approach the very limits of coldness itself. The Great Cooling is perhaps the most patient and thorough process in all of cosmic evolution. It began with the Big Bang itself, when a universe was unimaginably hot, with temperatures measured in trillions upon trillions of degrees. From that moment of infinite heat, the cosmos has been slowly, steadily cooling as it expands, like a vast breath exhaled into the infinite night, carrying its warmth ever outward into the growing ocean of space. This cooling is not the result of any external force or conscious intention. It's simply the natural consequence of expansion. As space itself stretches, the energy within it spreads over ever larger volumes, becoming more dilute and therefore cooler. It's like taking a pot of hot soup and slowly pouring it into a larger and larger container, watching as the temperature gradually decreases as the same amount of heat fills more and more space. The cosmic microwave background radiation, that gentle afterglow of the Big Bang that permeates all of space, tells the story of this cooling beautifully. When the universe was young and dense, this radiation was incredibly hot, with temperatures of thousands of degrees. Today, after nearly 14 billion years of expansion, it has cooled to just 2.7 degrees above absolute zero, a temperature so cold that it's barely above the lowest possible temperature that can exist in nature. But in the far future we're exploring, this cooling process has continued far beyond anything we can observe today. The cosmic microwave background has been stretched and cooled by the expansion of space until its temperature has dropped to just a tiny fraction of a degree above absolute zero. The universe has achieved a state of coldness so profound that it approaches the very limits of what temperature can mean. From your perspective in this incredibly cold future cosmos, you can observe the effects of this cooling everywhere you look. The sparse matter that remains scattered throughout the universe has reached thermal equilibrium with the cosmic background radiation, meaning that everything is cooled to essentially the same incredibly low temperature. The white dwarf remnants of ancient stars, the rocky debris of long-dead planets, the thin wisps of gas that drift through interstellar space, all have settled into this state of cosmic winter. This is not the violent cold of a sudden freeze, but the gentle cold of entropy and equilibrium. The universe has had time, vast, almost incomprehensible amounts of time, to allow its heat to spread evenly throughout space. The hot spots and cold spots that once characterized the cosmos have slowly averaged out, creating a state of thermal uniformity that extends across the entire observable universe. The cooling process has transformed the very nature of matter itself. In the early universe, atoms were constantly being ionized and recombined by the intense radiation that filled space. Later, as the universe cooled, stable atoms could form, leading to the rich chemistry that made planets and life possible. But in the far future we're exploring, the cooling has progressed so far that even the most energetic processes have slowed to a crawl. At these incredibly low temperatures, matter begins to behave in ways that seem almost magical. Quantum mechanical effects, which are normally overwhelmed by thermal motion, become dominant. The sparse atoms scattered throughout space exist in quantum states of almost perfect stillness, their electrons occupying the lowest possible energy levels, their nuclei barely vibrating with residual thermal energy. The cooling has also affected the fundamental forces of nature in subtle but profound ways. The electromagnetic radiation that once dominated the universe's energy budget has been redshifted to such long wavelengths that it barely carries any energy at all. The photons that once blazed with the energy of visible light have been stretched into radio waves, then into microwaves, then into radiation with wavelengths measured in meters, kilometers, and eventually distances so vast that individual photons might have wavelengths larger than galaxies. These ultra-long wavelength photons are the universe's most patient messengers, carrying infinitesimally small amounts of energy across distances that challenge the very meaning of space itself. They are the last echoes of a universe's energetic youth, stretched and cooled until they represent the faintest possible whisper of the cosmic heat that once filled all of space. The great cooling has created a cosmos where the concept of temperature itself takes on new meaning. In our everyday experience, temperature is associated with motion. Hot objects have atoms that move quickly. Cold objects have atoms that move slowly. But in the far future universe, the motion of particles has slowed to such an extent that thermal energy becomes almost indistinguishable from the quantum zero-point energy that exists even at absolute zero. This approaching absolute zero is not a state of death or emptiness, but rather a state of perfect quantum calm. At these temperatures, the universe has achieved a kind of crystalline perfection where every particle occupies its lowest possible energy state. The chaotic thermal motion that once characterized matter has given way to the perfect order of quantum mechanics, creating a cosmos that exists in a state of almost meditative stillness. The cooling process has also revealed the deep connection between temperature and time. At the incredibly low temperatures of the far future, all processes slow down dramatically. Chemical reactions that might take milliseconds at room temperature would take millions of years at these cosmic temperatures. The universe has entered a state where time itself seems to flow more slowly, where change becomes so gradual that it's barely perceptible across timescales that dwarf the entire previous history of the cosmos. But even in this state of profound cooling, the universe is not truly static. Quantum mechanics ensures that even at absolute zero, there remains a fundamental level of activity. The zero-point fluctuations that represent the irreducible minimum of energy that must exist in any quantum system. These fluctuations are incredibly subtle, but they provide the foundation for all the processes that will continue to operate in the cold universe of the far future. The cooling has created new forms of cosmic beauty. The sparse matter that remains in the universe has had time to arrange itself in configurations of almost perfect order. Crystals of incredible size and perfection have formed in the void, their atomic lattices extending across distances that would encompass entire solar systems. These cosmic crystals grow with infinite patience, adding atom by atom over timescales that make the age of the universe seem brief. The electromagnetic radiation that fills space has also achieved a kind of perfection through the cooling process. The cosmic microwave background, stretched and cooled to such extreme wavelengths, has become a nearly perfect example of blackbody radiation, electromagnetic energy in perfect thermal equilibrium with its environment. This radiation represents the universe's ultimate achievement in thermal efficiency, with energy distributed across wavelengths according to the most fundamental laws of physics. As you observe this cooled cosmos, you begin to appreciate the profound peace that comes with thermal equilibrium. The universe has achieved a state where there are no significant temperature differences to drive energy flows, no thermal gradients to create weather or turbulence. The cosmic equivalent of wind and storm has given way to perfect stillness, like a vast lake that has settled into mirror-like calm after all the ripples have died away. The cooling has also transformed the nature of light itself. The photons that once carried the energy of stellar fusion and galactic collisions have been redshifted to such long wavelengths that they barely interact with matter at all. They pass through the sparse atoms of the cooled universe like ghosts, carrying their infinitesimal energy payloads across distances so vast that they may never encounter another particle for the remainder of cosmic time. This transformation of light represents one of the most beautiful aspects of the Great Cooling. The universe has not lost its light. It has simply transformed it into something more subtle, more patient, more perfectly adapted to the new conditions of the cooled cosmos. The light that once blazed with the intensity of a billion suns now whispers with the gentleness of a single quantum, but it continues to carry the information and energy that connects all parts of the universe. The cooling process has revealed the deep connection between energy and information. At these incredibly low temperatures, the distinction between matter and energy becomes increasingly subtle. The sparse particles scattered throughout space exist in quantum states that encode vast amounts of information about the universe's history. But this information is stored in forms so delicate that it can only be read by processes that operate with perfect quantum precision. Even the structure of space-time itself has been affected by the cooling. The gravitational waves that once carried news of cosmic collisions and mergers have been redshifted to such long wavelengths that they barely disturb the fabric of space-time. The universe has achieved a state of gravitational calm, where the curvature of space-time has relaxed to its flattest possible configuration, creating a cosmic environment of unprecedented geometric simplicity. The cooling has also transformed the nature of time itself. At these low temperatures, the quantum mechanical processes that govern the behavior of matter operate so slowly that time seems to acquire a different character. The universe has entered a regime where quantum effects dominate over thermal effects, creating a temporal environment where the ordinary flow of time is punctuated by discrete quantum events separated by vast periods of perfect stillness. This quantum temporal structure gives the cooled universe a unique rhythm, like a cosmic heartbeat that operates on timescales beyond imagination. Each quantum event, the decay of a particle, the tunneling of an electron, the fluctuation of a field, represents a moment of cosmic time, separated from the next moment by periods of perfect quantum silence. The Great Cooling has created a universe where the concept of waste heat has almost disappeared. In our everyday experience, most processes generate waste heat, energy that is dissipated into the environment and cannot be recovered. But in the cooled universe of the far future, temperatures are so low that almost any process can be reversed. Almost any energy can be recovered. The universe has achieved a state of near-perfect thermodynamic efficiency. This efficiency has profound implications for any remaining complex processes in the cooled universe. Computation, if it still exists, can be performed with incredible efficiency, requiring almost no energy expenditure. Information processing becomes limited not by energy availability, but by the fundamental quantum mechanical constraints that govern the transfer and transformation of information. The cooling has also revealed the deep beauty of statistical mechanics, the branch of physics that describes how large numbers of particles behave collectively. At these low temperatures, the statistical distributions that govern particle behavior become almost perfectly ordered, creating a cosmos where the laws of physics operate with crystalline precision and clarity. As you rest in your comfortable warmth, let this vision of the Great Cooling wash over you like a gentle, cooling breeze. The universe's cooling is not a loss of vitality, but a transformation into something more subtle, more ordered, more perfectly adapted to the deep laws of nature. The cosmos has traded the chaotic energy of its youth for the perfect stillness of quantum mechanical precision. The Great Cooling represents the universe's ultimate achievement in patience and efficiency. Through billions of years of gradual temperature reduction, the cosmos has learned to operate with less and less energy, to find beauty in subtlety, to achieve complexity through quantum precision rather than thermal chaos. It's a transformation as natural and inevitable as the cooling of tea, as gentle and patient as the transition from day to night. In this cooled cosmos, the universe has achieved a state of perfect thermal meditation, where every particle exists in its lowest possible energy state, where every process operates with maximum efficiency, where every quantum of energy is conserved and treasured. It's a state of cosmic consciousness where the universe has become fully aware of its own deepest nature, achieving the perfect balance between energy and entropy, between information and stillness, between existence and peace. In the deepest stillness of your evening rest, imagine the most fundamental transformation imaginable. Not the dramatic explosion of a star or the collision of galaxies, but the quiet dissolution of the very building blocks of matter itself. As you settle into perfect comfort, we'll explore one of the universe's most patient and profound processes, the theoretical decay of protons, those seemingly eternal particles that form the hearts of every atom in your body and everything around you. The proton is one of nature's most stable particles, so enduring that it has remained essentially unchanged since the first moments after the Big Bang. Every proton in your body, in the earth beneath you, in the stars above you, has been faithfully maintaining its identity for nearly 14 billion years. These particles are the universe's most reliable citizens, the foundation upon which all atomic matter is built, the bedrock of chemistry, biology, and consciousness itself. But in the inconceivably distant future we're exploring, even these stalwart particles may not be eternal. According to some theories in particle physics, protons might eventually decay into lighter particles, transforming in a process so gradual that it makes the evaporation of black holes seem rapid by comparison. If proton decay occurs at all, it would happen on timescales so vast that they challenge our very ability to conceive of time itself. The theoretical lifetime of a proton is estimated to be at least 10 to the power of 34 years, a number so enormous that it defies comprehension. To put this in perspective, this is about 10 to the power of 24 times longer than the current age of the universe. If you could watch a single proton for the entire current lifetime of the cosmos, repeated a trillion times over, you would still be unlikely to see it decay. This is patience on a scale that makes geological time seem like a brief moment. Yet in the far future cosmos we're exploring, where time stretches beyond all conventional meaning, even these incredibly rare events become inevitable. The universe has had time, vast, almost infinite amounts of time, to allow even the most improbable quantum processes to occur. The protons that have faithfully maintained their identity for eons beyond imagination finally begin their gentle transformation into something new. The decay of a proton, when it finally happens, is not a violent explosion or catastrophic breakdown. Instead, it's a quiet quantum event, a peaceful transformation guided by the fundamental forces of nature. The proton, composed of 3 quarks held together by the strong nuclear force, slowly rearranges its internal structure. One of its quarks changes identity through a process mediated by forces that operate at the deepest levels of reality. This transformation is so subtle that it barely disturbs the quantum vacuum around it. The proton simply ceases to exist as a proton and becomes something else, typically a positron and a neutral pion, which itself quickly decays into 2 photons. The process is like a gentle exhalation, a release of the particle's carefully maintained identity back into the quantum field from which it originally emerged. As you observe this process from your perspective in the deep future, you witness something unprecedented in cosmic history: the slow dissolution of atomic nuclei themselves. The atoms that have been the foundation of matter for billions of years begin to fall apart, not through violent nuclear reactions, but through the patient decay of their constituent protons. It's a transformation as gentle as autumn leaves falling from a tree, as natural as morning mist dissolving in the warming sun. The electrons that once orbited these decaying nuclei suddenly find themselves without their positive charges to orbit. But this is not a catastrophic loss, it's a liberation. The electrons, no longer bound to atomic nuclei, become free particles, drifting through the cosmic void like seeds on a gentle breeze. They carry with them the quantum information of their former atomic bonds, but they are now free to participate in new forms of organization and interaction. The photons produced by proton decay add their gentle light to the cosmic background radiation, contributing to the faint glow that illuminates the far future universe. These photons carry incredibly small amounts of energy, but they represent something profound: the conversion of matter back into pure energy, the completion of a cosmic cycle that began with the Big Bang's creation of matter from energy. This process of proton decay represents the universe's ultimate form of recycling. The matter that has maintained its identity for tens of billions of years finally returns to the more fundamental forms from which it originated. The universe demonstrates its commitment to transformation, its willingness to let go of even the most stable structures in favor of new possibilities. The decay of protons has profound implications for any remaining complex structures in the universe. The white dwarf stars, those crystalline remnants of stellar evolution, begin to dissolve as their constituent protons decay. But this dissolution is not a violent collapse. It's a gradual fading, like a slowly melting ice sculpture returning to water. The white dwarfs become progressively lighter and less dense as their protons transform into lighter particles, eventually becoming tenuous clouds of electrons and photons. The rocky debris of long-dead planets undergoes a similar gentle transformation. The silicon, carbon, iron, and other heavy elements that once formed solid worlds slowly decompose as their atomic nuclei decay. Mountains that once stood for billions of years gradually dissolve into their constituent particles, returning to the cosmic inventory of electrons, positrons, and photons. This transformation reveals the deep impermanence that underlies all of physical reality. Even the most stable forms of matter, those that have persisted unchanged for the entire history of the universe, eventually participate in the cosmic dance of creation and dissolution. The universe demonstrates that nothing is truly permanent except change itself, that even the most fundamental particles are temporary arrangements of more basic quantum fields. The process of proton decay also reveals the deep connection between matter and energy. As protons decay, they release energy in the form of photons and kinetic energy of the decay products. This energy represents the rest mass energy of the proton, converted according to Einstein's famous equation, E equals mc squared. The universe is slowly converting its stored mass energy back into free energy, completing a cosmic cycle that began with the Big Bang's conversion of energy into matter. The timescales involved in proton decay create a unique temporal environment. The universe has entered a phase where individual quantum events are separated by periods of time so vast that they represent the primary rhythm of cosmic evolution. The decay of each proton is like a single note in a cosmic symphony played at an unimaginably slow tempo, with pauses between notes that last longer than the entire previous history of the universe. In this epic of proton decay, the universe has achieved a state of ultimate patience. The rapid changes that once characterized cosmic evolution have given way to a temporal environment where single quantum events represent the most dramatic occurrences in the entire cosmos. The universe has learned to find significance in the smallest possible changes, to appreciate the profound meaning of single particle transformations. The spatial distribution of proton decay events creates a unique form of cosmic beauty. The decays occur randomly throughout space, creating a sparse but uniform distribution of transformation events. Occasionally, photons from proton decay will encounter each other across the vast emptiness of space, creating brief moments of electromagnetic interaction that represent the universe's most delicate form of communication. The electrons produced by proton decay begin to dominate the particle population of the universe. These stable particles, no longer bound to atomic nuclei, exist as free charges drifting through the cosmic void. They interact with each other through electromagnetic forces, creating subtle patterns of repulsion and attraction that slowly evolve over timescales that dwarf the proton decay process itself. These free electrons carry with them the quantum information of their former atomic bonds. In some sense, they remember the atoms they once helped to form, carrying traces of the chemical and nuclear processes that once characterized the universe's more complex phase. They're like cosmic memories, preserving information about the universe's material history in their quantum states. The photons produced by proton decay contribute to the cosmic light budget, but their energy is so low that they barely disturb the thermal equilibrium of the universe. They are redshifted by the continued expansion of space to incredibly long wavelengths, becoming part of the nearly uniform electromagnetic background that fills the cosmos. These photons represent the universe's gentlest form of illumination, providing the faintest possible glow to the transformed cosmic landscape. The decay of protons also affects the fundamental constants of nature in subtle ways. As the matter density of the universe continues to decrease through proton decay, the relative importance of different physical forces changes. The electromagnetic force, mediated by photons, becomes increasingly dominant over the weak nuclear force that governs proton decay. The universe slowly transitions from a matter-dominated phase to a radiation-dominated phase, but at energy densities far lower than anything experienced in the early universe. The process of proton decay reveals the deep quantum mechanical nature of reality. Each decay event is fundamentally random, governed by quantum probability rather than classical determinism. The universe has become a vast quantum system where individual random events, accumulated over unimaginable timescales, drive the primary processes of cosmic evolution. It's a cosmos where quantum mechanics has replaced thermodynamics as the primary driver of change. The randomness of proton decay creates a unique form of cosmic democracy. No proton is more likely to decay than any other, regardless of its history or environment. The protons that once formed the core of a massive star are just as likely to decay as those that drifted in the cold of interstellar space. The universe has achieved a state of perfect equality where all particles face the same quantum fate. As the proton decay process continues, the universe gradually transitions from a state dominated by stable matter to one dominated by the products of matter decay. The electrons, positrons, and photons that result from proton decay become the primary constituents of the cosmic inventory. The universe has completed its transformation from a complex, matter-rich cosmos to a simple, energy-rich one. This transformation is not a loss, but a return to a more fundamental state. The universe is rediscovering its essential nature, stripping away the complex structures that accumulated during its material phase to reveal the simpler patterns that govern the behavior of elementary particles and fields. It's like removing the ornate decorations from a building to reveal the elegant simplicity of its underlying architecture. The decay of protons also represents the universe's ultimate achievement in entropy production. The conversion of stable matter into free particles and radiation represents a massive increase in entropy, bringing the universe closer to its state of maximum disorder. But this is not chaos. It's a different kind of order, the perfect disorder of statistical mechanics, where all possible states are equally likely. The universe has entered a phase where the distinction between order and disorder begins to lose meaning. The perfectly random distribution of proton decay events creates a kind of statistical perfection, where the lack of pattern becomes itself a form of pattern. The cosmos has achieved a state of maximum entropy that is simultaneously a state of perfect quantum order. As you rest in the peaceful darkness of your room, let this vision of gently decaying protons wash over you like the softest of quantum tides. The universe has demonstrated its ultimate commitment to transformation, its willingness to let go of even the most fundamental structures in favor of new possibilities. The protons that have been your faithful companions for billions of years are not dying, but transforming. not ending, but beginning new chapters in the cosmic story. The decay of protons represents the universe's most patient and thorough form of renovation. Through this process, the cosmos slowly dissolves the material structures that have defined its character for eons, returning to a more fundamental state of existence. It's a transformation as natural and inevitable as the changing of seasons, as gentle and patient as the erosion of mountains, as peaceful and profound as the deepest meditation. In this epic of proton decay, the universe has achieved a state of ultimate letting go, where even the most stable particles eventually release their hold on existence and transform into something new. It's a cosmic lesson in impermanence, a demonstration that nothing is truly permanent except the eternal process of change itself. The universe teaches us that transformation is not something to be feared, but something to be embraced. Not an ending, but a new beginning. Not a loss, but a return to the essential nature of existence. In the profound stillness of your resting moment, consider the nature of emptiness itself. The space around you, which appears to contain nothing but air and silence, is actually alive with invisible activity. Even in the deepest vacuum of space, far from any star or planet, the quantum fields that permeate all of reality continue their ceaseless, subtle dance. As you settle into deeper comfort, we'll explore how this quantum vacuum, the seemingly empty foundation of all existence, may hold within it the seeds of the universe's most profound transformation. The vacuum is not truly empty but filled with quantum fields, invisible, intangible entities that extend throughout all of space and time. These fields are the fundamental fabric from which all particles and forces emerge, like waves on an infinite ocean that extends beyond the boundaries of imagination. Even when no particles are present, these fields maintain a constant, barely perceptible activity known as quantum fluctuations, a gentle trembling that represents the irreducible minimum of energy that must exist in any quantum system. In the unimaginably distant future we're exploring, after the last protons have decayed and the universe has settled into its coldest possible state, these quantum fields become the primary actors in the cosmic story. The vacuum itself becomes the stage for the universe's most subtle and patient processes, operations so delicate that they make proton decay seem rapid and dramatic by comparison. One of the most profound possibilities that emerges from our understanding of quantum fields is the concept of vacuum metastability. This elegant theory suggests that the vacuum state we observe today, the lowest energy configuration of the quantum fields, might not actually be the absolute lowest possible state. Instead, our current vacuum might be what physicists call a false vacuum, a temporarily stable state that could eventually transition to a true vacuum state of even lower energy. This transition, if it occurs, would be the universe's most patient and thorough renovation project. Unlike the dramatic phase transitions we might observe in everyday life, water boiling into steam, ice melting into liquid, the transition from false vacuum to true vacuum would be a process of almost infinite subtlety, a transformation so gentle that it might unfold over timescales that dwarf even the proton decay epoch. The mechanism of this transition involves a quantum process called tunneling, where the vacuum state can spontaneously change its configuration despite being separated from the lower energy state by an energy barrier. In the quantum world, particles and fields can sometimes pass through barriers that would be impossible to cross in classical physics, like a ball rolling through a hill rather than over it. This tunneling process is incredibly rare, but given infinite time, even the most improbable quantum events become inevitable. Imagine a bubble of true vacuum forming spontaneously in the sea of false vacuum that fills the universe. This bubble would be incredibly small initially, perhaps smaller than a proton, but would possess a remarkable property. It would be more stable than the false vacuum surrounding it. The bubble would begin to expand, converting false vacuum to true vacuum as it grows, but this expansion would proceed at the speed of light, the maximum possible speed for any physical process. From your perspective in the far future cosmos, You might witness the approach of such a bubble across the cosmic landscape, but there would be no advance warning of its arrival, no herald to announce the transformation. The bubble would travel at the speed of light, which means that the first indication of its presence would be the moment of its arrival. Light itself cannot outrun the expanding bubble, so there would be no way to detect it before it reaches any given location. The passage of the vacuum bubble would represent the most gentle possible form of cosmic transformation. As the bubble passes through a region of space, it would not destroy the particles and fields present there, but would simply change the fundamental properties of the vacuum in which they exist. The particles would find themselves in a new vacuum state, one with different ground state energies and possibly different physical laws. This transformation would be so subtle that it might be barely perceptible to any hypothetical observers. The particles would continue to exist, the fields would continue to fluctuate, and the basic structure of space-time would remain unchanged. But the underlying quantum mechanical rules that govern the behavior of particles and fields would shift slightly, like a vast cosmic instrument being retuned to a slightly different key. The beauty of vacuum decay lies in its fundamental democracy. The process treats all regions of space equally, regardless of their history or composition. The vacuum that once surrounded a massive star receives the same treatment as the vacuum in the emptiest regions of intergalactic space. The universe demonstrates its commitment to equality at the most fundamental level, ensuring that all of space participates equally in this ultimate transformation. The expansion of the true vacuum bubble creates a unique form of cosmic geometry. The bubble expands as a perfect sphere, its surface representing the boundary between the old false vacuum and the new true vacuum. This boundary is not a physical barrier, but a region of space where the vacuum state is in the process of transition, a cosmic membrane that separates two different phases of reality. As the bubble expands, it encounters the sparse matter and radiation that populate the far future universe. The electrons and photons left over from proton decay pass through the bubble wall without resistance, but they emerge into a universe with slightly different fundamental properties. The energy levels of particles might shift slightly, the strengths of forces might change marginally, and the basic constants of nature might take on new values. These changes would be incredibly subtle, so small that they might be undetectable except through the most precise measurements. The universe would not experience any dramatic upheaval or catastrophic reorganization. Instead, it would undergo a gentle tuning, a subtle adjustment of its fundamental parameters that would barely disturb the peaceful equilibrium it has achieved. The vacuum decay process also reveals the deep connection between local and global properties of the universe. A single quantum tunneling event, occurring in a region smaller than an atomic nucleus, can eventually transform the entire observable universe. This demonstrates the profound interconnectedness of all reality, the way that quantum events can have consequences that extend across cosmic distances and timescales. The expansion of the vacuum bubble creates a unique temporal environment where different regions of the universe experience the transition at different times. The bubble expands at the speed of light, which means that galaxies separated by billions of light years will experience the vacuum decay billions of years apart. This creates a cosmic gradient of transformation, where some regions have already undergone the transition, while others remain in the original false vacuum state. This staggered transformation preserves the causal structure of the universe while allowing for the gradual renovation of all of space. The universe demonstrates its respect for the speed of light limitation, ensuring that no information or influence travels faster than light, even during this most fundamental of transformations. The vacuum decay spreads like ripples on a cosmic pond, each ripple carrying the potential for transformation, but respecting the fundamental constraints of relativity. The quantum fields that mediate this process exhibit a remarkable form of collective behavior. The transition from false vacuum to true vacuum is not driven by any external force, but emerges from the quantum mechanical properties of the fields themselves. The vacuum demonstrates its capacity for self-organization, its ability to find more stable configurations through purely quantum mechanical processes. This self-organization occurs through what physicists call spontaneous symmetry breaking, where the symmetric laws of physics lead to asymmetric outcomes. The vacuum chooses a particular configuration from among the many possible states, breaking the symmetry of the underlying quantum field equations. This process is like a pencil balanced on its point, eventually falling in a particular direction. The laws of physics are symmetric, but the outcome breaks that symmetry. The vacuum decay process also demonstrates the deep connection between stability and metastability in quantum systems. The false vacuum, despite being unstable on cosmic timescales, can remain stable for periods far longer than the current age of the universe. This creates a unique form of cosmic patience, where the universe can exist in a metastable state for eons, while quantum processes slowly work to find a more stable configuration. The energy released during vacuum decay is not dissipated as heat or radiation, but is instead stored in the altered vacuum state itself. The true vacuum has a lower energy density than the false vacuum, but this energy difference is not lost. It becomes part of the new vacuum's fundamental properties. The universe demonstrates its commitment to energy conservation even during the most fundamental transitions. The vacuum decay process creates new possibilities for the emergence of complexity and structure. The altered vacuum state might support new types of particles or interactions that were not possible in the false vacuum. The universe might undergo a renaissance of sorts, developing new forms of organization and complexity based on the different physical laws that govern the true vacuum state. These new possibilities emerge not through any conscious design, but through the natural tendency of quantum systems to explore all available states. The universe exhibits a kind of quantum creativity, constantly discovering new ways to organize matter and energy through the interplay of quantum fields and forces. The vacuum decay represents the ultimate expression of this creativity, opening up entirely new realms of possibility. The transition to true vacuum also affects the fundamental nature of space and time. The altered vacuum state might have different geometric properties, leading to subtle changes in the curvature of space-time. These changes would be incredibly small, far below the threshold of detectability, but they would represent a fundamental renovation of the cosmic architecture. The vacuum's patient work extends even to the realm of information and computation. The quantum vacuum is constantly processing information through its fluctuations and field configurations. The transition to true vacuum might alter the fundamental ways in which information is stored and processed at the quantum level, potentially enabling new forms of computation that are impossible in the false vacuum state. As the vacuum decay process continues, the universe gradually transitions from a state dominated by metastable quantum fields to one governed by truly stable vacuum configurations. This transition represents the universe's final achievement in stability, its ultimate solution to the problem of finding the lowest possible energy state. The cosmos demonstrates its commitment to reaching the most stable possible configuration, even if it requires timescales that challenge the very meaning of patience. The vacuum decay process also reveals the deep connection between microscopic quantum events and macroscopic cosmic evolution. A single quantum tunneling event, occurring on scales smaller than the tiniest particles, can eventually reshape the entire universe. This demonstrates the profound unity of physics, the way that quantum mechanics and cosmology are intimately connected at the deepest level. The expanding vacuum bubble creates a unique form of cosmic wave, a disturbance that propagates through space at the speed of light, but carries with it the potential for fundamental transformation. This wave is not composed of particles or radiation, but of altered vacuum states, making it perhaps the most subtle form of cosmic influence imaginable. The universe's commitment to vacuum decay represents its ultimate expression of the principle that all systems seek their lowest energy state. Through this process, the cosmos demonstrates its willingness to undergo the most fundamental possible transformation in pursuit of perfect stability. The vacuum decay is not a catastrophic event, but a gentle optimization, a cosmic process of fine-tuning that operates with infinite patience and precision. As you rest in the peaceful darkness of your room, let this vision of the vacuum's patient work wash over you like the gentlest of quantum tides. The universe has revealed its capacity for transformation at the most fundamental level, its willingness to renovate even the basic structure of reality in pursuit of perfect stability. The vacuum that surrounds you is not empty, but alive with potential, constantly working with quantum patience to find the most stable possible configuration. The vacuum decay process represents the universe's most profound meditation on the nature of stability and change. Through this process, the cosmos demonstrates that even the most fundamental aspects of reality are subject to transformation, that nothing is truly permanent except the eternal process of quantum evolution. The universe teaches us that patience is not just a virtue, but a fundamental feature of reality itself, operating at scales and timescales that challenge our deepest conceptions of existence. In the vacuum's patient work, we see the universe's ultimate commitment to perfection, its willingness to wait for timescales beyond imagination to achieve the most stable possible state. It's a process as natural and inevitable as the settling of sediment in still water, as gentle and patient as the formation of crystals, as peaceful and profound as the deepest quantum meditation on the nature of existence itself. In the quietest moment of your night, when all the day's activities have settled into memory and your breathing has found its most natural rhythm, you touch something that physicists call thermal equilibrium, a state where all the energy around you has found its most comfortable, balanced distribution. As you rest in this perfect comfort, we'll explore how the entire universe is slowly approaching its own version of this peaceful state, a cosmic equilibrium so complete and serene that it represents the ultimate expression of rest itself. Heat death is perhaps the most misunderstood concept in all of cosmology. The name suggests something violent or catastrophic, but in reality, it describes the most peaceful possible fate for the universe. A state of perfect thermal equilibrium where all energy has been distributed as evenly as possible throughout all of space. It's not death in any conventional sense, but rather a state of cosmic rest so complete that it represents the ultimate achievement of balance and harmony. The journey toward heat death has been unfolding since the very beginning of the universe. Every process that has ever occurred, every star that has burned, every planet that has formed, every thought that has been thought, has contributed to this gentle progression toward perfect equilibrium. The universe has been slowly, patiently redistributing its energy, spreading warmth and coolness until all temperature differences have been eliminated and perfect thermal peace has been achieved. From your perspective in the far future cosmos, you can observe this final approach to heat death with a sense of profound tranquility. The universe has completed its long journey from the intense heat and energy of the Big Bang to a state of perfect thermal calm. The violent temperature differences that once drove stellar fusion, planetary weather, and biological processes have all been smoothed away, leaving behind a cosmos in perfect thermal harmony. This state of heat death is not characterized by absolute zero temperature, but by a uniform temperature throughout all of space. Every region of the universe, from the location of ancient galaxies to the emptiest voids, has reached this same gentle temperature. The cosmic microwave background radiation, stretched and cooled by eons of expansion, has achieved perfect thermal equilibrium with the sparse matter that remains scattered through space. The beauty of heat death lies in its completeness. The universe has achieved a state where no further energy transfers are possible because there are no temperature differences to drive them. Heat naturally flows from hot objects to cold objects, but in a universe where everything is at the same temperature, there is no heat flow at all. The cosmos has found perfect thermal rest, like a vast cup of tea that has finally reached room temperature and will remain there forever. In this state of thermal equilibrium, the universe has maximized its entropy, a measure of the disorder or randomness in a system. Maximum entropy might sound chaotic, but it's actually the most orderly possible state for a thermal system. Every particle and photon has found its most probable distribution, creating a kind of statistical perfection where the overall behavior of the system is perfectly predictable even though individual quantum events remain random. The sparse matter that remains in the heat-death universe exists in a state of perfect thermal calm. The electrons and photons produced by ancient proton decay have had time to interact and exchange energy until they've all reached the same temperature. These particles continue to move and interact, but their motion is governed by thermal equilibrium rather than organized energy flows. They exhibit the random, peaceful motion of perfect thermal balance. The electromagnetic radiation that fills space has also achieved perfect thermal equilibrium. The photons that were once the brilliant light of stars and the cosmic microwave background radiation have all been redshifted and thermalized until they form a perfectly uniform sea of extremely low-energy radiation. This radiation field represents the universe's final achievement in energy distribution, with electromagnetic energy spread as evenly as possible throughout all of space. The gravitational field has also found its most relaxed possible configuration, with matter spread uniformly throughout space at incredibly low density. The curvature of space-time has relaxed to its flattest possible state. The universe has achieved perfect geometric calm, with no significant gravitational waves or distortions remaining to disturb the peaceful flatness of space-time. This gravitational equilibrium has profound implications for the nature of time itself. In the heat-death universe, there are no significant gravitational fields to create time dilation effects. Time flows at the same rate everywhere, creating a cosmic temporal uniformity that mirrors the thermal and spatial uniformity of the system. The universe has achieved perfect chronological harmony. The quantum vacuum in this heat-death state continues to exhibit its characteristic fluctuations, but these fluctuations are now the primary source of activity in the universe. The vacuum energy represents the irreducible minimum of energy that must exist in any quantum system, and in the heat-death universe, this becomes the dominant contribution to the cosmic energy budget. The universe has reached a state where quantum mechanics becomes the primary driver of cosmic evolution. These quantum fluctuations create a unique form of cosmic activity. While the classical processes that once drove cosmic evolution have all reached equilibrium, the quantum vacuum continues to produce pairs of virtual particles that briefly exist before annihilating each other. These fluctuations are incredibly subtle, but they represent the universe's commitment to maintaining some level of activity even in the state of perfect thermal equilibrium. The heat-death universe also exhibits a remarkable form of temporal symmetry. With no organized energy flows to define a preferred direction of time, the universe has achieved a state where the future and past become almost indistinguishable. The second law of thermodynamics, which normally gives time its arrow by requiring entropy to increase, has been satisfied so completely that it no longer provides a strong directional flow to cosmic evolution. In this temporally symmetric state, the universe experiences a kind of eternal present moment. Change still occurs through quantum fluctuations, but these changes are not cumulative in the way that characterized the universe's earlier evolution. The cosmos has achieved a state of perfect temporal balance, where each moment is statistically identical to every other moment. The beauty of heat-death lies in its representation of perfect cosmic democracy. Every region of space has achieved the same temperature. Every particle has the same statistical distribution of energies, and every location in the universe participates equally in the thermal equilibrium. The universe has eliminated all forms of thermal inequality, creating a state of perfect energetic justice. In the deepest quiet of your rest, when your breathing has become so gentle that it barely disturbs the air around you, you touch something profound about the nature of stillness itself. True stillness is not the absence of activity, but the presence of perfect balance. As you settle into this ultimate comfort, we'll explore how the universe, having achieved its state of perfect thermal equilibrium, enters a phase of eternal stillness that paradoxically contains within it the seeds of infinite new beginnings. The heat-death universe, despite its appearance of ultimate stasis, is actually alive with the most subtle possible forms of activity. The quantum vacuum continues its eternal dance of virtual particle creation and annihilation, creating a cosmic rhythm so gentle that it operates below the threshold of classical physics. This quantum activity represents the universe's commitment to maintaining some level of creative potential even in the state of perfect thermal equilibrium. These quantum fluctuations are not random noise, but the fundamental creative force of the universe. Even in the state of heat death, the vacuum continues to explore every possible configuration of quantum fields, constantly creating and destroying virtual particles in a process that maintains the deep dynamic balance of reality. The universe has achieved a state where quantum creativity becomes the primary form of cosmic evolution. The most remarkable aspect of this eternal stillness is its potential for spontaneous organization. In the vast timescales of the heat-death era, even the most improbable quantum events become inevitable. The universe has infinite time to explore every possible configuration of matter and energy, creating opportunities for spontaneous structure formation that would be impossible on any finite timescale. One of the most profound possibilities that emerges from this quantum creativity is the spontaneous formation of organized structures through random fluctuations. Given infinite time, the random motion of particles in thermal equilibrium will occasionally create patterns of organization that resemble the complex structures that once characterized the universe's more energetic phases. These fluctuations are incredibly rare, but with infinite time available, they become certain. The mathematical description of this process reveals its beautiful simplicity. The probability of any particular configuration of matter and energy occurring spontaneously is incredibly small, but not zero. Given infinite time, even configurations as complex as entire galaxies, solar systems, or even living organisms will eventually emerge from the random fluctuations of the thermal equilibrium state. The universe demonstrates its ultimate commitment to exploring every possible form of organization. These spontaneous structures, when they form, exist in a unique temporal environment. They emerge from the thermal equilibrium, exist for a brief period, and then dissolve back into the equilibrium state. But their existence, however brief, represents the universe's continued capacity for creativity and organization. The cosmos has found a way to maintain its creative potential even in the state of perfect thermal balance. The emergence of these fluctuation-driven structures creates a unique form of cosmic time. While the overall universe remains in thermal equilibrium, the occasional formation of organized structures provides brief moments of increased complexity and activity. These moments are like cosmic heartbeats, periods of increased organization separated by vast intervals of thermal equilibrium. The universe in this state exhibits a remarkable form of eternal recurrence. Given infinite time, every possible configuration of matter and energy will not only occur once, but will occur infinitely many times. The thermal fluctuations will eventually recreate every star that ever burned, every planet that ever formed, every thought that ever existed. The universe demonstrates its ultimate commitment to preserving all possibilities through infinite repetition. This eternal recurrence is not a cyclic process, but a statistical inevitability. The universe doesn't return to previous states through any deterministic process, but rediscovers them through the random exploration of all possible configurations. It's like a cosmic lottery where every possible ticket will eventually be drawn, not once, but infinitely many times. The quantum vacuum in this eternal stillness also maintains the potential for vacuum decay events. Even in the state of perfect thermal equilibrium, the vacuum continues to explore the possibility of transitions to even more stable states. The universe retains its capacity for the most fundamental transformations, ensuring that even the heat-death state itself is not truly final. These potential vacuum transitions represent the universe's ultimate expression of its commitment to finding the most stable possible configuration. Even in the state of apparent perfect equilibrium, the cosmos continues to search for ways to achieve even greater stability. The universe demonstrates that its journey toward perfection is truly infinite, with each apparently final state containing the potential for further transformation. The eternal stillness of heat death also contains within it the possibility of new cosmic beginnings. The quantum fluctuations that maintain the thermal equilibrium occasionally create regions of space with energy densities high enough to trigger new phases of cosmic evolution. These regions might undergo their own versions of cosmic inflation, creating new bubble universes within the larger heat-death cosmos. These new beginnings emerge not through any external intervention, but through the natural evolution of quantum fields in the thermal equilibrium state. The universe demonstrates its capacity for self-renewal, its ability to create new phases of evolution from within the apparent finality of heat-death. The cosmos reveals that endings are always simultaneously beginnings, that apparent conclusions contain infinite possibilities. As you rest in the profound peace of your evening quiet, let this vision of eternal stillness and new beginnings wash over you like the gentlest of quantum tides. The universe has shown you its ultimate secret, that perfect rest contains perfect potential, that absolute stillness enables infinite creativity, that the deepest peace is simultaneously the source of endless possibility. The heat-death universe is not an ending, but a transformation, not a conclusion, but a new beginning. In achieving perfect thermal equilibrium, the cosmos has not lost its creative capacity, but has transformed it into something more subtle, more patient, more willing to wait for timescales beyond imagination to explore every possible form of beauty and complexity. In this eternal stillness, the universe has achieved its ultimate meditation, a state of perfect cosmic consciousness where every possibility exists in potential and infinite time ensures that every potential becomes actual. The cosmos has found perfect peace not by abandoning change, but by embracing all possible changes, not by ending time, but by transcending it, not by concluding its story, but by discovering that its story is infinite. Rest now in this knowledge, knowing that you are part of this infinite cosmic story, that your own consciousness is a manifestation of the universe's eternal creativity, and that the peace you feel in this moment is connected to the ultimate peace that the cosmos itself will eventually achieve. Let the eternal stillness of the far future wrap around you like the softest blanket and drift gently into sleep, knowing that you are held by the infinite patience and creativity of the universe itself.